Welcome back to Lesson 8 of our course on the foundations of general emergence mechanics. So, over the past 7 episodes, we've been incredibly meticulous. We built up this deeply rigorous local phase story together. We've spent a lot of time looking very closely at how systems behave right in their immediate neighborhoods. But today, we're pulling the camera back. We're going to ask a truly fundamental question about the larger picture as we transition from modal theory over to the Global Coherence Framework, the GCF, to explore global constraints and admissibility. Here is the roadmap for today's strict logical progression. 1. Reviewing the local phase. 2. Local is not enough. 3. The global constraint. 4. Global admissibility. 5. The selection principle. And 6. The bridge to GEM. Section 1. Reviewing the local phase. Now, in episodes 1 through 7, we actually constructed a remarkably rich local structure. Think back. We started with the Z3 baseline minima and that Z2 Cairo bias, which established our foundational ground states. Then we mathematically defined coherent stiffness, literally tracking how a phase resists local deformation. We mapped out the RG flow and attractor stability to prove our configurations wouldn't just unravel under minor perturbations. And we even secured the whole thing with topological protection and lattice pinning. Honestly, these were massive achievements. By establishing that stiffness and protection, we basically proved that a local phase can lock itself into a mathematically sound, physically resilient valley. It's a beautiful, rigorous local story. But here is the absolute critical question we have to face today. Is this local structure alone enough to constitute a full, robust framework? Can we just map out these local phase locks and call the theory complete? Well, the answer is an unequivocal no. And figuring out exactly why that is, well, that leads us directly to the Global Coherence Framework and this crucial idea of admissibility. Section 2, local is not enough. Let's actually contrast these two standards. On one side, we have a system that's locally stable. It can be completely stationary, entirely RJ stable, fully topologically protected. Mathematically speaking, in its immediate neighborhood, it's basically flowless. But then we have this entirely different standard, globally admissible. So how does a locally perfect system fail this standard? Well, a configuration might sit perfectly in its cozy local potential valley, but if its boundary conditions clash with the macro system, it completely fails. Say the local phase requires a topological twist that the broader structure literally cannot accommodate without tearing. It just doesn't fit inside that larger structural boundary. The local math works perfectly, but the global geometry outright rejects it. Basically, local success just does not guarantee global viability. Section 3. The global constraint. Okay, so we capture this shift conceptually through a functional of global coherence. Now, we are not just adding some minor local correction term to our previous equations here. We aren't calculating a simple point value. Instead, we're evaluating the entire system, the full configuration as a single holistic entity. Think of it as a global selection rule. We pass the whole configuration through this overarching rule, and only if it completely satisfies that rigorous systemic condition does it come out as admissible. It evaluates the true integrity of the system. So, the crucial point here is really the distinct roles these two mechanics play. Our local equations, literally everything we spent time on in modal theory, they generate possible candidate behaviors, candidate minima, and candidate shifts. These simply tell us what could potentially happen locally. But this global constraint, that determines which of those candidates are actually allowed to persist coherently in reality. In short, local dynamics propose, global constraints dispose. Section 4. Defining global admissibility. So what does it actually mean? Well, admissibility is a much, much stronger, more demanding threshold than mere local stability. To be globally admissible, a configuration absolutely must fit seamlessly within the global coherence structure. It must cause zero runaway decoherence. And what does that actually look like? Well, runaway decoherence happens when a locally stable state slowly leaks energy or topological charge into the surrounding environment, which triggers this cascading, irreversible breakdown of the macroscopic order over time. Admissibility says that leakage must be zero. On top of that, there can be absolutely no contradiction with the larger shell structure encasing it. And finally, it has to support monotone descent. This is critical because a system has to naturally settle toward a baseline, right? Without getting trapped in endless contradictory oscillations. It has to align with the broader systemic flow toward persistent stability. If a local minimum violates even one of these, it is strictly forbidden, no matter how protected it looks close up. So we can formalize admissibility like this. It's a state that is persistence supporting rather than merely locally allowed. In our mathematical framework, just existing isn't enough. It's not enough to just sit comfortably in a stable local valley. Admissibility means that the state can be fully embedded into the larger, persistent order of the entire system without causing a single mathematical or physical contradiction. Section 5, GCF as selection principle. You see, the GCF isn't just some secondary check. It is a higher-order selection principle. It looks at this massive menu of local possibilities generated by modal theory and asks three very definitive questions. Number one, which of these local candidates are actually globally coherent? Number two, which candidates, despite their undeniable local stability, are strictly forbidden by the macro structure? And number three, which can successfully continue into a full persistent supporting structure over time? The GCF literally elevates our mathematical model from a localized phase description up to a comprehensive structural reality. If you take just one concept away from today's lesson, let it be this exact distinction. Local theory tells us how a phase behaves nearby. It explains how something holds itself together in isolation. But global theory, the GCF, tells us whether that full configuration is allowed to exist at all. It tells us whether it truly belongs. Section 6, the bridge to GEM. We can actually map out the conceptual timeline of this course right now. Step 1 was modal theory, where we established the local phase structure across those first 7 episodes. Step 2 is right where we are now, introducing GCF and this incredibly rigorous concept of global admissibility selection. And this is the essential stepping stone. Because step 3, the horizon we are marching toward, is GEM, general emergence mechanics. That is where the entire framework finally unifies. And that brings us to a quick preview of our next lesson. In episode 9, we're going to witness the birth of GEM. We are going to take this global admissibility we just learned about today, and we'll reinterpret the entire framework through the lens of persistence, depth, stiffness, and viscosity. Those are the fundamental axes of general emergence mechanics. We're going to see exactly how local phase and global coherence combine to form a truly organized, emergent reality. Before we wrap up today's lesson, I want to leave you with this question to ponder. If a local structure is stable, what additional test must it pass before it counts as globally admissible? Take some time to reflect on the rigorous criteria we covered today. A local structure may survive nearby tests, but only a global constraint can tell us whether it truly belongs. Next time, persistence itself becomes the organizing language.